Welcome to the Exudyn basic tutorial. I'm happy to have you here now for some minutes to show you some basic introduction into Exudyn. So to get started, we will go to the homepage first. So whenever we just search for Exudyn, let's say GitHub, then we will go to the basic page of Exudyn on GitHub, which contains all the information, so the documentation, large amount of documentation files, demos, and so on, as well as the code, Python packages, C++ source code, all kinds of things that you need to build it or to study it. There's a short README file. The README file will just give you some current updates. So we have version 1.7.104 here, which is a development version. Last stable release was 1.70. And there's also a Twitter account. And yeah, is also mentioned for easy install. We just have to do pip install Exudyn for a Python package. As if you have Python already, then you're quite familiar with that. There's a lot of external packages that we can link to, ngSolve for finite elements, OpenAI, robotics. It's using PyBind 11 heavily on the background. For scientific papers, I would be happy if you cite us with this link, recent paper. And yeah, to get into it, of course, you can watch the YouTube channel, but there is a lot of documentation. So there's read the docs and GitHub pages, but I recommend read the docs. And there is a PDF file, which contains basically all information. Let's get started with that one. So it's a quite tiny PDF file, but it has around 900 pages with all reference, manual, descriptions, and so on. So you can just download this file and go through the pages, but we are not doing that today. The easier way is to go to read the docs. And here you would have on the left-hand side all the basic information, similar as in the GitHub page to get started with. And then we can have a look at the code itself. We can go to the Get Started page to see what is Exudyn. It's a flexible multiple dynamics code. The quite old origin of the code, but the code is just 5 years old now. It's intended to build complex multiply models consisting of rigid and flexible bodies for mechatronic systems, robotics, whatever application you have. It's still developed. There's many features already, and it is intended to be used in a very versatile way. And of course, you can develop it also on the C++ side. It's fully open source, no closed paths exist for it. There's a lot of papers related to it. And if you want to install it, there are some installation instructions. So it works with Python. So you need a Python version. And we tested it with many Anaconda versions. The current one is Python 3.11 with Spider 5 and Anaconda from 2023. There may always be newer versions then, and usually they work without any problems. Yeah, if you have Anaconda, so first you should get one. We can just, let's say, download Anaconda, and if you go to this download, you can just download it here, and it will download a gigabyte at least of data, and you install it. Takes some minutes time, and then you would have Python. You could also then add Python environments to work with different Python versions. But this is up to you then. I'm working with Conda environments on Windows, but also on Linux, and both works quite well with Exudyn. As soon as you have Anaconda, you need an editor. I'm using Spider, but you can also use Visual Studio Code. or 2-byter. All of them work well with Exudyn. And so if you have that installed, you can open Spider. You find it in the Windows. When it is installed, it looks like that. And you can then build models here. Alternatively, you could also use Visual Studio Code. It works very similar, and I'm just preferring Spider here. So then you have to install Exudyn. So if you go to an Anaconda prompt, how to Anaconda shell, here I'm working with the base environment, then I can just say pip install Exudyn. Sorry. And if you don't have it installed yet, then it will install this version. And if you want to have a very new version, you can also install it with the --pre version to get the latest Exudyn package installed. So let's try this as well. So we can uninstall Exudyn again, and we can also install the newer version. In your case, this might make sense because you might use the newest features of Exudyn. So this will install now the 104 micro version, and doing that, we can now put Exudyn here, and then let's see if we have the correct version. And you see it's already here. Sometimes you have to restart the Spider. Now the idea is to build up a very simple model of a mass and a spring. So we first have to import Exudyn. Usually we import it as abbreviated term exo. Then we have to import the utilities. We just import everything. We could also do it another way. So having that done, we can just create a system container, which is the basic tool to work with. You see, type completion takes sometimes some time to get started, but then you get everything type completed. So the system container, we just add a new system, so we can work with several systems at the same time to do some different tasks with each subsystem, and we just add them to the system container. So this is the basic way to go, but here we usually just need one multi-body system. So this is the system now we work with, and everything before, we can just forget about it, and you could always copy paste this because you will always need that. Now, in order to create a mass with a damper, we just build a ground object, and we have some new nice functionalities, which are create functions that create, like now, the ground and return back the ground object number. We could also add here a flag that would say we would like to get some additional data, then this would be extended here. And now to add a mass, we just do a very similar thing. So we have the mass point, create function, create. We can just choose from this list, create a mass point. We can give it a name now. So here you see the whole list of things we have here, right? The reference position, which is the position where we place the mass. We can give it an initial displacement, velocity. We need to give it a mass. We can attach gravity, which adds a load, and give it some drawing features. So let's call this just heavy mass, and the reference position would be then, let's say, 200. Have it not put at 000, so ground will be always reference to 000. And doing that, we also need to add the physics mass. So let's say this is 12 kilogram. And we add gravity and say this is acting in minus y direction. And finally, we also give it draw size. Let's say this is 0.2 meter for the drawing. And as I said, we can just either do a standard return value, which gives us the object number, or we could also return the full dictionary, which returns more information about the created object. And we can add a color. Let's letting it show in this color. So it will then draw a sphere for the mass point. Now this is already everything we need. So even we don't need the ground, but this is for later on. And then we could just say assemble and solve dynamic. And this is enough to run the whole thing. So we can go here and press the run button or press F5, and this will run the model and it's finished. So we don't see very much actually, but we could then do and call the solution viewer, do it here in the IPython. And doing that will open the solution viewer that will show the model. Maybe not as we expected, but what we see is more or less that we have a mass point created with a load, and it just falls down in direction of gravity, as we expected. So we would like to improve this a little bit. So there's a lot of options, and the first thing that we do is we add some visualization settings for the node. And this would say that we don't draw it as a point, but we draw it as a sphere now. And the second thing is we would like to add some world bases in order to see the reference point. And now we could just, let's say, add an initial velocity. Let's say 550, which would now let this sphere be thrown as we know it from physics courses. And again, we run the solution viewer, and we will see now this sphere going up and then going down. So let's start this again. So you see, as we expect, the free motion of a sphere with initial velocity. Okay. So quitting this dialog, we can always press Q, key Q, or just quitting it. Now, this is not very exciting, so let's get rid of this initial velocity. And we would like to add now some spring damper. So we again use these create functions. And with the create function, we just need a body list. And we add the ground and the mass as the two bodies between the spring damper. And then there's a lot of options, but in fact we just need to take some stiffness. Let's take 500 here. A damping, let's take 10. And we can also add some drawing. Let's say draw size equals 0.1. And this would now add a spring damper. And as we release the mass with a position 2, 0, 0, and the ground is at 0, 0, 0, this would give us a pendulum-like motion of the whole system. So we can just copy this up to here And what we also did not specify so far, we can add some simulation settings. So this is a predefined structure with several hundreds of settings, and then we just adjust the main settings that we need, which is the time integration. So first we can add some verbose mode to see some output. And we would also like to set some end time. And we would also like to set some steps. And for that, we need some step size. And let's define it here now. So let's say tn equals 10 seconds and step size equals 0.02, for example. This is influencing the time integration, so that means smaller gives more accurate results. And in fact, if you want to determine the accuracy, you just have to refine that step size and up to the value where you see that your accuracy is met. So with that, we have to pass on this simulation settings here to the dynamic solver. And with that, we can now run it again. And yeah, whenever the solution viewer opens, by the way, this is already solved. So that means everything is solved. Now we see it here. It was saying, well, Exudyn solver started, solving 500 steps. They took like 10 milliseconds to solve it. And now we can visualize the solution. It's loaded then, and we see the mass under attached to a spring under gravity and moving like a pendulum, which is damped. So after some time, it will damp out. And yeah, if you would run it longer, let's do that. Let's say 100 seconds, right? And we could do this again. And let's see now if we make it a little bit faster, then we would see that the motion is damped. Of course, it takes a very long time to be damped out, but we see that it's kind of damped motion and the angle becomes smaller and smaller. Okay, so as you see, it's really simple. Yeah, you just have to build a system, add your tools. We could go to the documentation for that. So if you have to create mass point function, we would go again to the documentation, and there we would find the create mass point function that tells us in detail how this works. So the function is creating 2D or even 3D mass points. It has these parameters, they are all described. There's usually an example that shows you how it works. And it's also showing in which examples this is used. So you can just check these examples, like this one. Let's click on it, and then you get to the GitHub page where this example is shown up, and you can download all the examples just from GitHub, however you like that. And yeah, the whole structure is given here. So it's this Python C++ command interface, and here are these so-called main system extensions, and all these functions are given here. So you can just go through it and see which kind of functions are available in which kind of structure, like the system container or the main system. They all have certain functionality, which is then described here, and especially then there are advanced functions. And so for the next tutorial, we will go into more detail. So we don't use then these functions, which are just very simplified functions, but we will look in the back end of these functions, how they work. This is then for next time. So thanks a lot for watching. First step, getting into Exudyn, and I hope to see you next time. Have a great day.